Today's lesson, we're looking at section 6.1 and really looking at atoms, elements, and compounds. So, really, kind of the composition of matter. And one of the things that we'll look at is some of those terms and vocabulary that you used back in ninth grade in physical science. So, one of the first terms that we'll look at, just kind of using your notes that I've provided in class for you, is matter. And matter, we know, it occupies space and it has mass. That's one distinction. And then we throw the other term, mass, and that's just how much matter or material an object has. And then the third one we throw in there is weight. Weight is the use of, or we use the term gravity, and it's the force of gravity pulling on objects. So those three terms are what were introduced back in ninth grade in physical science, and I throw those at you today as well, just as a point of reference. I don't know if it's all that important for us as it was back in ninth grade to distinguish all three of those, but we'll use those interchangeably. So I think it's important for us to at least clarify the difference between the three terms. So one of the first things I wanted to do, however, is look at this biochemistry. Biochemistry is the biology and the chemistry involved within that of living things. And so if we look at the microscopic level and then below that, we'll get to the atomic level. So here we'll look at some of the important atoms and molecules important for living things and how they sustain themselves and the chemical reactions involved within those living cells and living organisms. So one of the terms that, again, I'll introduce here that's on your sheets is molecules. Molecules are the smallest particles of substances, retaining those properties, and it's usually two or more atoms involved there. So the diagram that I have below there is of caffeine. I've had a couple cups of coffee myself, and most of us are usually having some form of caffeine throughout the day, whether it's through a chocolate bar, maybe even a cup of coffee or some type of drink that you might consume. But what you'll notice is that this is a model, and this model has these atoms that we're going to look at and how they connect with each other, which we refer to as bonds. And one of the fun properties that we get to do is not only look at these models, but we also get to construct them. So this is just that written portion, that verbiage that's in your textbook, found in page 6.1, pages 148 through about 156 of your chapter text. Well, back in physical science, we use this chart. This is called the periodic table of elements, and it has most of the elements that you maybe are familiar with or have certainly seen in other science classes, especially physical science. You'll notice some common ones that are essential for our studies. And of course, those are hydrogen, carbon, nitrogen, and oxygen. And those are really kind of on the top of the periodic table. Most of you remember some of those memories of physical science where you had to maybe look at some of the properties in some of the columns and even some of the characteristics of certain elements on this chart. We're going to focus on four of those, and I'll get to those in a moment. But just wanted to give you some familiarity with that. Remember that kind of where this green section is going down between the green and the aqua blue. So this segment on the far right-hand side here are the nonmetals, and that actually includes this blue one over here of hydrogen. And then from the green on all the way to the magnesiums in orange and the sodiums in reds, these are all metals. So we have two groups. We have the metals and the nonmetals on the periodic table. Again, we point that as a reference. We don't necessarily, that's not necessarily our focus. All right, so these elements, we know that are the simplest form. They're the simplest kind of matter. And we know that there are 100 plus that exist. And really, when we think about it, at least in the sense of biology, just 30 of these are really important for life. And only four is going to be our focus. So again, we'll use this as a point of reference. Your textbook also has a periodic table of elements chart that we'll point as a reference to as well. And that's on page 149. All right. So, what is this section about? Well, atoms and molecules. One in particular, an atom is the smallest unit of an element, and it has all those characteristics. So, certainly, if we point out like an element like carbon, it is made up of an atom, and we can break that down into some known quantities that we've discovered over years. And as part of the physical science and chemistry that you'll have taken or will take to break down maybe even more into some of the history. But let's look at some of those elements that and break those down. So an atom has an electron, it has a proton, and it has a neutron. Remember back to those days where we mentioned that electrons have a negative charge, protons a positive, and neutrons are neutral. And I've highlighted those in just different colors to emphasize that. Two of these can be found within the central core. So if you look at the diagram down below, you'll notice that the yellow and orange, there is a plus sign, and then the orange doesn't have anything. This is the neutrons. The positives are my protons, and they're all in the center of the atom. That means this is the nucleus. And it's a term that we've used before, but this neutron or this nucleus, excuse me, has these elements that have mass. And then you'll notice there's a ring around this, and this ring has these negative charges, and these are our electrons. So here's where you can find each of those: the electrons, those ones on the outer edge, and we have shells or energy levels that we describe that as, and then we have some in the core that don't go anywhere, but that's in the nucleus, and that's our protons and neutrons. So, what do you remember from that junior high science class you had? You remember we looked at the periodic table, and I have one behind me here. There was this atomic number, and really the atomic number tells us the number of protons. And if we know the number of protons, we'll also look at it. It tells us the number of electrons as well. So it tells us some good information. Um, there is another experience that we had in physical science where we looked at the mass number, and that is the mass of that particular atom, and that is a combination of the number of protons and the number of neutrons. Remember, those are at the center of an atom. Another term that is oftentimes thrown out here, and you may not have remembered, but I'll put it up here anyways, is called an ion. And an ion is a positive or negative charge of an atom. And the reason is that when atoms are historically neutral, so in other words, if you look at hydrogen or carbon or oxygen, they're a neutral atom. In other words, the positive and negative charges are equal to one another. So, for the example, carbon has 6 protons, in other words, 6 positive charges. That also means that it has 6 negative charges so that they're equal to one another. An ion means that it's either gained an electron or it's lost an electron. In other words, it's either gained a negative charge or it's lost a negative charge. And that's what we refer to as an ion. So the fourth term that I'll throw out here, that again, we're calling this from physical science, that will help explain some of the information that will move forward, is something called an isotope. You might have remembered the prefix iso refers to equal, like an isosceles triangle. So an isotope in this case is where you have atoms of the same element, for example, carbon, but they have different numbers of neutrons. Now, we've seen this before, for example, when we look at evolution. Evolution, we use carbon as an example of carbon dating. And when we date carbon, we know that there are two forms. There's a form called carbon 12, and there's a form called carbon 14. Really, they're both carbon. The difference is the number of neutrons each one has. In other words, one has 2 more neutrons. And so instead of 6 neutrons, which carbon 12 has, carbon 14 has 8. So 8 plus 6 protons and neutrons is a total of 14, whereas carbon 12 has 6 protons, 6 neutrons, or a total of 12, which would be the mass. So an isotope has just these varying forms, and we've seen it before. This brings out why atoms would join another one. In other words, form a bond. Well, there are two major types of bonds. The first one is up on the screen in blue, and it's called an ionic bond. Now, remember what an ion is. An ion means that it's either gained or lost electrons. So, hence, when we look at a bond, it gives us the definition of this. So, when one atom donates electrons to another atom, it leads to a positive and negative charge of a particular atom. Remember, atoms are attracted to each other because it needs to find some stability. An atom is neutral, but it's not stable. And what I mean by that is if you look in the bottom here where you can see the sodium atom and the chlorine atom, notice the sodium on the outer shells here, we have these electrons. And that's important because if you remember from earlier years, in these shells can contain 2 electrons in the first energy level, a total of 8 in the second, and a total of 8 in the third. Well, if it only has, in this case, sodium only has 1 electron in the outer energy level, it's not stable. In other words, it's either got to lose that electron to become stable, or it's got to gain maybe 7 more. In this particular case, it's going to lose that electron. That's the easiest route. Well, luckily, chlorine has 2 in that first energy level. It has 8 in that second energy level. And in the third, it has 7. So this is an easy fit. One will, you can notice it will be transferred to the other. When that happens, what is going to occur is you get an ion. In other words, an ion is either a positive charge or a negative charge. So on the far right side of this arrow, right here where the equation is, we're going to form this bond, and the bond that exists between sodium and chlorine is called sodium chloride or table salt. And table salt is an example of this ionic bond, which allows these atoms, they were neutral, but they just weren't stable. So now this is stable. So bonds allow atoms to become stable. And that's an important element of this. So if you need some more information on this particular one, if you look at ionic bonds on page 153 of your text, you'll notice some more examples of sodium chlorine and a little more description in the paragraphs that are provided. So overall, as I mentioned, this molecule is neutral, and that leads us to the next type of bond, which is a covalent bond. And covalent bonds have the ability to share. I always like to think of this one as the prefix co up here with the blue CO. Co refers to like a co-worker. In other words, it's a combination of two. And these two are equally sharing maybe jobs or responsibilities. Now, again, just like the previous ionic bond, a molecule would form a covalent bond because it's not stable. It's neutral, but not stable. Covalent bonds typically form when you have two nonmetals that are forming. And for our purposes, our 4 major elements are all going to be, ironically, nonmetals: hydrogen, carbon, oxygen, and nitrogen. So let's look at 2 of those, carbon and nitrogen down below here, and which are, carbon and hydrogen. So carbon and hydrogen can form these bonds where if you look at the periodic table, hydrogen has 1 electron on its outer shell, but it needs another one. Carbon, on the other hand, has 2 in the first energy level that aren't shown here, and then it has 4 in the outer shell, which it needs 4 more to be stable. Well, luckily, it can form 4 bonds with hydrogen to get those 4 other electrons needed. And when it does so, it shares those between the hydrogen and the carbon fairly equally, where you get this bond, which we refer to as a covalent bond, where there's a sharing effect. In this case, there are 4 shared connections between the hydrogen and the carbon. So, what this leads to is the most common biological bonds in nature, which are, in our case, are all going to be nonmetals. I said hydrogen was one. Hydrogen makes up about 10% of us. A second is oxygen. Oxygen makes about 65% of all the elements in our body. Nitrogen has about 3% of all these bonds that exist and these molecules that exist in our bodies. And then, of course, carbon. Carbon is about 18%. Now, if you look at these 4 elements, you'll notice that it has these little dashes or lines. For example, hydrogen has one dash. And what that tells me as a biologist is that there is one bond that it can combine with to become stable. Oxygen, however, has two. It needs two bonds to become stable. Nitrogen would require three, and then therefore carbon needs four bonds in order to become stable. Now, again, all these elements are neutral; they just need to become stable. And when that happens, you get these unique blends of molecules that are combining with each other, forming these covalent bonds. The unique thing about this is if you look at some of the sci-fi shows, they're referring to carbon or living things being carbon-based life forms. In other words, all living things that we are aware of contain carbon, and that's in our universe. So when we go exploring places currently, we're looking for carbon-based life forms and even the presence of water for life to exist. So 96% of all living things are made up of hydrogen, oxygen, carbon, and nitrogen. So we refer to this as HONC or HONC. I'll go back to that HONC, HONC. Now, what I'm going to suggest and look at is some of the times when we make these models between these four elements, students often at times ask, well, I made this model, is this possible? Or what is its name? So on one of the sheets that I've given you is the ability to kind of look at something and make that decision for yourself. In other words, we're going to say if something is stable or unstable. If it's unstable, it won't exist in nature. If it's stable, that means that the bonds that exist between those elements allows it to exist in nature, potentially. And so if we have some models like this, where we're using hydrogen, oxygen, nitrogen, carbon, we just need to count the number of covalent bonds or those little lines between those atoms. And so just keep this in mind, both on the handout that I will give you or have given you, and also the models we make in class, that hydrogen bonds with one, oxygen two, nitrogen three, and carbon four. So if we have the wrong number, for example, if we see that oxygen is combining with another oxygen, like here in the middle on the left-hand side, this would be a stable molecule. In other words, each oxygen needs two lines to become stable. So let's move to the next molecule here, where we have an oxygen and a carbon. And again, oxygen needs two, and I see those that are present. Carbon needs four. And so on the other side, you can see those two lines indicating a bond between that and happens to be another oxygen. And what you'll notice here is I have on purpose put a little hydrogen next to it. This molecule to the right is unstable. In other words, it would never exist because this hydrogen, that would be correct, it could bond with one, but oxygen can only bond with two. So this one would never exist. The one on the left, the oxygen, is called oxygen gas, and that's a stable molecule that would exist. So stable and unstable. All right. Finally, if we look at water as an example, we said that water was necessary for life. Now, water has some unique properties, and water's ability to bond with in other words, oxygen with two hydrogen molecules, give it some unique properties in nature. We just came through or just entering the spring season with winter behind us now. And what we're noticing is that the ice is melted on our area lakes, but that's a unique property. In other words, water is solidifying on the top, and below that is typically a liquid form, and that allows plant life and fish life or organisms in Minnesota to survive the winter because they're not going to freeze physically in the flowing water below. So the unique properties about water is number one, it has the ability to share two unpaired electrons. And when it does, we call these polar covalent bonds. So a little bit different. And these polar covalent bonds exist because if you look at the diagram, remember hydrogen needs one extra electron and oxygen needs two. So in this case, we would form maybe a little line between this oxygen molecule and the first hydrogen. And here's the oxygen with the second line going to the hydrogen. So this seems to work. However, they're not equal in their sharing. It's like if you're sharing your cookie with maybe your friend and you eat 75% and you give your friend 25% of the cookie, you're sharing, it's just not equal. And same thing here. Water has the ability to share these electrons, but it's really not that equal. And what happens is that the electrons are held a little closer to the oxygen, so it makes it seem like there's two extra electrons on the oxygen molecule, and it seems like there's a lack of electrons on the hydrogens. So near the bottom here of my hydrogens, we give it a positive charge because in a sense, there is more of a positive charge on that side. And then on the top side of oxygen, there are no positive pieces to this. And so it has more of a negative charge. So one end is negative, and the other end on the hydrogen side is positive. And that's where we get something called in chemistry electronegativity, where the oxygen is holding those electrons a little bit closer. It's kind of being selfish. So this slight charge allows it to have some unique properties and allows water to actually expand as it freezes and condense as it goes into its solid form or its liquid form, which is from a solid to a liquid, which is just the opposite normally of most matter. Lastly, if we look at pH, this is something that we'll look at as far as how it has the ability to measure and look at it as far as its sustainability for life. But that'll be for another video. Thank you, everybody.